All right, so we're going to be looking at the check your understanding questions from lesson 2. So first question here, we are going to be calculating a left Riemann sum with 5 equal subintervals to approximate the area of the region between x equals -1 and x equals 4. So the graph we're going to be looking at here is this function y equals e to the x. So I'm going to go ahead and create a graph of that from -1 to 4. Just kind of an approximation of what this might look like. So from -1 all the way over to 4. And again, I'm just kind of estimating sort of what this graph might look like. It's an exponential graph, so it's going to curve up like that and kind of flatten along the x-axis there. So it's not an exact graph, but this is what we're looking at. And we're going to be using a left Riemann sum with 5 equal subintervals. So we need to split this up from -1 to 4 into 5 equal subintervals. So we can use that formula b minus a divided by n, sort of calculate that, where b represents the end of our interval and a represents the beginning of our interval and n represents the number of intervals we have. So in this case, we would have 4 minus -1 divided by 5, which is 5 over 5, which means 1. Each of our subintervals is going to have a width of 1 unit. And we can see that here on the graph, right? 1, 2, 3, 4, 5 subintervals, and each of those would have a width of 1. Okay, so let's go ahead and draw in what these rectangles would look like. So these rectangles would have a height that would match on the left side of them. Let me draw a line over and then line down. And then the left side of the interval for the height, and then over, and then down. Left side of the interval for the height, over, down. Left side of the interval for the height, over, down. And then the left side of our interval for our height, over, and down. So this is the area that we'd be calculating with a LRAM method. You can see that these rectangles are giving us an under approximation, right? We're missing this little area here, 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 and obviously right here, a bigger section. But that always happens when you have an increasing function and you're using a left-hand method. Now, if we elected, instead of doing a left-hand method, if we wanted to use, say, a right-hand method, let's just show the difference. I'll kind of overlay what that would look like. So we would set our interval on the height of our rectangles based on the right side of our interval. We draw that over, and then we go down. So this is the difference between these two. Look at the difference between these two rectangles, right? The right side gives us a fairly large over approximation, right? This is too much area, versus the left side, which we drew in before, gave us a fairly large under approximation. Neither of them is ideal, but that's what we have. All right, so let's go ahead and go to calculating this. So the width of our interval is 1, and then we would multiply it by the height. So that would be plugging in the x value there at the left side of our interval, so -1, so it'd be e to the -1, plus, again, 1, because that's the width of our interval, times the height, which is going to be located at 0 this time, so e to the 0 power, plus 1 times e to the first, that would be our height here, and then plus 1 times e to the second, that would correspond with our height right here, times 1, again giving us the area of these rectangles, and then finally our last one, 1 times e to the third, because our height is right here at e to the third, and then width of 1. So right here is our calculation of the area. Obviously, each of these subintervals is 1 unit in width, and then these calculations here are the height at the various places where we're calculating the height of these rectangles. Now, you may notice we did stop at 3, which is a little confusing because we're going all the way up to 4, but 3 is the left side of that last interval that goes between 3 and 4. And since we're using a left Riemann sum, that's going to be the last value there. and -1 is the left side of that first interval. And you can see that we do have 5 equal subintervals that we're calculating. Interact with that? Yes, let me interact with that. So we got, I'm going to leave off all those ones because those aren't really going to do anything in terms of our calculation, but we have e to the -1 plus e to the 0 plus e to the 1 plus e to the second plus e to the third. So I got my approximate value there. I'll go ahead and round that to 3 decimal places, remember, because we're doing AP exam rounding. So 31.56, 31.561. That is approximately equal to 31.561 units. That is our area approximation. And again, just quickly, this would be a slight under approximation, right? Because we can see this is an increasing graph and we're using a left-hand sum and we are missing some area here, right? This area, this area, this area, right? And even a small amount down here, right? We are missing some areas there. We are slightly underestimating the area. Cool. All right. Next question. So same scenario, but now we're going to be using a midpoint Riemann sum approximation with 5 equal subintervals. So rather than aligning the height of our rectangles with the left endpoint there where it hits the graph, we're going to go into the middle and have that middle section hit the graph. So let me just show how that looks slightly different visually. A lot of times these things really help to see visually. So even if you can make a rough sketch, it's kind of a useful strategy. Okay, exponential function. Let me redo that. Okay, that'll be fine. Okay, so because we're doing midpoints, our height of our rectangle is going to be aligned with the midpoint of each of these subintervals, right? And we're still doing 5 of them, but this midpoint, that's where we're going to be drawing our rectangle to. You'll notice now that a little piece of the rectangle may be above the graph and a little piece of rectangle may be below the graph. So now we're not necessarily having an underestimate or an overestimate. We may actually be right on. It's hard to tell. So again, the height of a rectangle goes with the midpoint here. Okay, right here at the midpoint. So kind of trickier to draw versus the endpoints. But again, it's even more pronounced on this side. You can see that we have a little section that's actually above the graph. We also have a little bit under the graph there. So this is kind of hard to tell whether this is actually an overestimate or an underestimate, or if it actually is really accurate. Kind of hard to know. All right. So these are what our rectangles would look like in this situation, and we need to calculate the area of these. Now, just like last time, the width of all of these intervals are going to be exactly 1 unit, right? So we have 1. But these x values that the height is located at in all of these scenarios is going to be slightly different. So we need to figure out these heights based on the x value that they're located at. Okay, so I'm just sketching those in there. So the first one would be 1 times, and this would be located at e to the -1/2, or -0.5. So it has a width of 1, and then the height would be e to the -0.5, because that's going to be where the midpoint of that interval is. And the height located is the point on the graph there. Okay, and so this one would be located at 0.5/2. So 1 times e to the 0.5. Plus, now this one's 1 times e to the 1.5. That's where the middle of that interval is. Plus 1, that's again our width is 1, times e to the 2.5. And finally, plus 1 times e to the 3.5. And again, those are our 5 intervals, right? 1, 2, 3, 4, 5. Never bad to kind of count those up again. Make sure you didn't accidentally include like 6 intervals or 4 intervals, right? Because you want to make sure you're doing 5 in this case. Alrighty, so let me go ahead and pull back up Desmos. So we'll just make some small edits to that previous calculation. to kind of show that. All right, so let me just go ahead and hit small edits to that. It's negative 0.5, 0.5, 1.5, 2.5. Okay, made some small edits there, and we do have our calculation of 52.035. Round that to 3 decimal places, so 52.035. Did I calculate that correctly? Let me go back to there, and that's so much bigger than the previous one. So let me just go ahead and double check that I did actually do that correctly here. All right, let me go back here, make sure we didn't mess up one of these. Yeah, okay. Looks like I don't see any errors there. Just was a little bit suspicious of that because we got a vastly different number. It's hard to see that this amount of little error here, this amount of underestimating was so far off of this one. Now, it's possible that this kind of overestimating now that we've kind of possibly introduced in like this section here, 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 or whatever has now created this to be an overestimate. But yeah, that's what we got for that midpoint Riemann sum. Again, pretty different answers there. So it would be nice to have, what's the exact answer, but we're not quite there yet. All right, let's go ahead and move on. All righty, question number 2. The rate at which water flows out of a pipe in gallons per hour is given by the function RT. Selected values of RT are shown in this table here. Use a Wright-Riemann sum approximation with 4 equal subintervals to approximate the area underneath R of t from t equals 0 to t equals 24. Okay, so a couple things here. We need to do 4 equal subintervals on the interval 0 to 24. Okay, so you may already kind of be able to do this, right? This is an interval that's 24 units long. And if you want to divide that into 4 equal subintervals, that's going to be 6 units each. But if these numbers weren't so easy to work with, we could still do our calculation of the end of our interval minus the beginning of our interval divided by how many intervals we want. And that's going to give us how big each of our intervals are. So it's going to be 6 units in this case, which is what we said before. So our first interval would go from 0 to 6. Our next interval would go from 6 to 12, and then from 12 to 18, and then 18 to 24, right? So these are kind of our intervals, so to speak, already kind of lined up there. We are using a right-hand Riemann sum approximation. So we're using the right side of that interval there to sort of calculate this out. We don't really need to do a picture on that, but just keeping in mind, right? We have 0, 6, 12, 18, 24. The heights of our intervals are going to be based on the right side value, right? So our interval from 0 to 6, the height of that rectangle is going to be calculated by the value that's on the right side, so the output at 6. And then for this one, it's going to be calculated by the output here at 12, and then the output at 18, right? And then the output at 24. So these are going to be how we calculate the height of our rectangles. Again, I have no idea if these rectangles are all accurate. I'm just sketching out random stuff. But again, the height of it is dictated by the right-hand side of the interval. Cool. All right. So for the first one here, our first interval from 0 to 6, again, the width of the interval is 6 units wide times the output at 6 here, which is 10.8. So that's going to be the height of our first rectangle. Width of 6, output at 6, which was 10.8, plus, again, another width of 6 times the output here at 12, which would be 11.4, plus another one width of 6, right, 6 units here, plus times the output at 18, which is 10.7, And then finally, this last rectangle here, again, width of 6 times the output at 24, which is 9.6. So I'm going to go ahead and calculate all that. I'm doing it here off to the side. So we have 6 times 10.8. Now, something you can do here, right, since everything is multiplied by 6, you can do 6 times and then add up all those values there. So 6 times 10.8 plus 11.4 plus 10.7 plus 9.6. So I'm adding up all those values and then multiplying them all by 6. And so I get a total Riemann sum approximation of 255. So 255. 255 what? Right? 255 what? So when you are doing a Riemann sum or an area under the curve in general, the units of this are going to be the units of your output, right? So which are gallons. So gallons per hour times the units of your input, so times hours, right? Because that's what we're doing here in all these calculations. The width of our interval are in hours, so hours, times the height of our interval, which is in this case, gallons per hour. So we're multiplying hours times gallons per hour, giving us gallons, right? So what's happening is this is giving us the amount of water that is flowing through the pipe in gallons. This is a measurement in gallons. So in summary, what does that mean? Let me go ahead and just kind of type this out real quick. The amount of water that flowed out of a pipe between t equals 0 and t equals 24. Right? So we're saying that between these times, a total of 255 gallons of water flowed out of this pipe. Cool. Alrighty, we're going to go ahead and look at a little bit more here, just kind of some general information about Riemann sums. So what are Riemann sums? They're an approximation of the area under the curve using rectangles, or in the future we may look at some other shapes like trapezoids. In a left-hand Riemann sum, we approximate the areas using the left side of the interval to determine the height where it hits the function value. In a right-hand Riemann sum, we use the right side of the interval to determine where it hits the function there. And then finally, in a midpoint Riemann sum, we use the middle, the exact middle of our intervals, and where that is, that gives us the height of our rectangles. Now, we can also use some other shapes, which we're going to look at later on, like trapezoids. You can see how these trapezoids can do an even better job than rectangles at kind of approximating the area. This is kind of much closer than any of the other approximations that you can see here before, right? Even the midpoint, which is pretty good, this one's probably better, right? In this case, we use the area of trapezoids. Okay. Basically, for any of these approximations, the more rectangles we use, the closer our approximation is. And you can see here going from 4 subintervals to more, 4 to 12, something like that, and then to an even greater number, there's less error, right? We have very big sections of overestimate here, much smaller ones here, and then tiny little minuscule overestimate here. It's still an overestimate, but it's much closer to the actual area. So the more subintervals we use, the more accurate our approximations are going to be. Anyway, that's just some basic information about Riemann sums and how they work. All right, let's stop there. See you guys later.